Well, thank you. So quickly to the Hasso-Plattner Institute. It's a computer science software institute just outside of Berlin in Potsdam. And we're extremely excited about the collaboration here. I think this is really a good sort of complementary expertise, having a medical center and software and AI expertise that we have. So now you've already met Pieter Abbeel. It's my pleasure to formally sort of introduce him. So he's a professor and director of the Robot Learning Lab at UC Berkeley. He is a co-founder of many companies, including Covariant, Greatscope. He is advisors to companies and, for example, the not-for-profit OpenAI. He's a founding facility partner at AI at the House and many other AI and robotics startups. So his research focuses on robotics and machine learning, in particular making robots learn from people, how to make robots learn through their own trial and error, and how to speed up skill acquisition through learning to learn. His robots have learned advanced helicopter aerobatics, knot tying, basic assembly, organizing laundry, locomotion, vision-based robotic manipulation. He has won plenty of awards, but I'm really excited to give the stage to him, and maybe he will tell us more about these cool things that he's been doing.
Thank you, Christoph, for the very nice introduction, and it's a real pleasure to be here. I hope we can build some connections and do some work together in the future. And actually, it's one of the most special places for me to be because both my nieces and my nephew were born here 1.5 years, 3.5 years, and 5 years ago. So very excited to be here. Now, if we think about AI, a simple question you could ask, well, should be able to see, right, if it's an intelligent system. So if you give it a picture like this, should be able to say that's a coffee mug. Very easy for us. But actually, if you think about computers, it's much harder because computers don't see the way we see. They see a bunch of numbers. And to make sense of this grid of numbers is actually very hard. It's actually not even clear how to write code that says if this number is bigger than that number, then it's a mug, and otherwise it's not a mug. And so people, of course, didn't succeed at doing it that way. What happened is people tried to look at machine learning instead. And for the longest time, people would apply machine learning in conjunction with domain expertise. So they would say, image, change the lighting conditions, all the pixels change. But what if I look at the edges in the image instead of the image itself? Oh, the edges are going to stay in the same place when I change the lighting conditions. So maybe that's more robust. And so people came up with a lot of more robust representations of images, fed them into things like support vector machines, which you can think of as the counterpart of linear regression. Linear regression, you fit a bunch of points with a line. If the points are roughly on a line, you have success. If they're not roughly on a line, it'll fall short. Same thing was happening here. These robuster representations of images, when fed into a support vector machine, was not good enough a representation to succeed and understand what's in an image. Then in 2012, out of Jeff Hinton's lab at the University of Toronto, everything changed. They showed that instead of a lot of engineering followed by a bit of machine learning, you should just machine learn the whole thing. And so put down a gigantic neural network and train the whole thing all the way from pixels to decision of what's in the image. Now, you might wonder exactly what's happening there. Well, a neural network consists of a bunch of neurons, just like, mainly inspired by the brain. Each neuron is pretty simple. A bunch of inputs get processed, put something out. But if you build a large enough network of neurons, that network can capture any input-output pattern. Now, how will it capture it? It will capture it by adjusting the strength of the connections between the neurons. And so then the name of the game becomes, how do you find the right strengths of connections between these neurons such that, indeed, you say dog for this and not cat? Doing this by hand is impractical. So the way it's done is by collecting a lot of data. And we talked about this earlier. What this means in this case, you get a bunch of images of cats, a bunch of images of dogs, a bunch of images of cars. You feed them in one at a time. And initially, the image goes in, and out comes the wrong decision because you didn't wire the network correctly. But then a backpropagation happens in the network that changes the strengths of the connections between the neurons. And now we'll understand that this is a dog. You repeat this for the next image, next image, next image. And then something magical happens. It doesn't just memorize the images you've shown it. it starts recognizing the underlying pattern in those images and can recognize what's in a new image it's never seen before. Well, how big of a breakthrough was this at the time? There's a big competition in image recognition called ImageNet. And the organizers have a secret stash of images, and you don't get access to those. All you get to do is send in your computer program, and they'll run it over their secret images, and then report out the error rate of your computer program. And so in 2010, the best entry in the competition had about 30% error rate. In 2011, not much better. And in fact, this was largely flatlining with the traditional computer vision approaches. But then out of Jeff Hinton's group, it was shown that by training a deep network, you can actually halve the error rate. And it wasn't just a one-time thing. People realized this methodology is more powerful than what they were doing before, switched methodologies, and we actually saw a very rapid acceleration in progress. And by now, this competition has been retired because human-level error rates have been achieved. Now, to be clear, that doesn't mean we have computers that have human-level vision, but for this type of image recognition problem, recognizing into 1,000 categories of this kind of data, human-level error rates have been achieved. Now, same thing actually happened in speech recognition. In there is a sequence of numbers corresponding to pressure in the air. Out is a transcription. Traditional approaches were not really making much progress anymore, but by training a large neural network with enough data, it was possible to break right through that, and in fact, also out of Jeff Hinton's group. And a little later, actually, Jeff and his students ended up at Google and built the latest generation machine translation system, also based on training large neural networks on pairs of things. Input sentence in one language, output sentence in another language. So what really happened under the hood is a change in programming paradigm. The way you used to program is you program by writing lines of code, might look like this. But to recognize that's a mug, that's not going to really work. What's happening now is say, well, the program really lives inside the network. A layer in a network can be seen as parallel compute. The next layer is the next serial part of the computation. It's a combination of parallel and serial compute. The code that's being run is encoded in the weights that are the strengths of the connections between the neurons. And the way you find the code is by feeding enough examples, inputs, and outputs that it needs to learn to recognize. For AI-type problems, this actually works much, much better than directly trying to write lines of code. And in fact, I would say much of the name of the game at this point is, can you collect enough data? Because the new way of programming becomes data collection of inputs and outputs. If you can collect the right data, feed it through, see where it still fails, based on that, collect more data, get it annotated, and repeat. And so that process is essentially the new programming at this point. It's not entirely true. There's a lot of things you need to know about how to architect a network and so forth, but at a high level, it's really collecting that data iteratively until you have your problem solved. So what I described so far, though, is just one kind of learning. It's deep supervised learning. Deep means that you're training a deep neural network. Supervised means that you train it from data where you have an input and an output always paired together. So you're always told, for this input, this should be the output. And I would say that's the thing that works. And if you want a working system today, that's probably the thing you would try to rely upon and get a lot of data to try to get it to work. But there are other types of learning that are also starting to work and that you might need in the future. First one is deep reinforcement learning. So if you think about deep supervised learning, input-output pattern recognition, it's not really intelligence that we think of as what it means to be intelligent. When you think about real intelligence, you think about achieving goals, something that understands when I see this and then act that way, I'm getting closer to my goals. So how do we build systems that try to achieve goals? One place where you might want to apply this is home robotics. What we're watching here is a video of a robot doing a lot of the chores that many of us wish robots could be doing for us. Now there's a catch, and the catch is that this robot is being teleoperated. So somebody is actually orchestrating every single motion this robot is making. But what it also shows is that it's really just the AI software that's missing. The hardware is there. We can have home robots as long as we can actually make them intelligent enough. And of course, students like to serve themselves beer this way. Now, this is for the home, but we actually have very similar systems in medicine. The Vinci system is pretty much the same as what you just watched. Somebody is teleoperating a robot, and the robot is doing the physical interaction, but a person is the brain behind all of it. The question is, can we make the robot think for itself? what do we need for that? Well, what we need is a system, could be a robot, could be other systems that perceive the world, act based on what they see, realize the world's going to change as a consequence, perceive again, and go in this feedback loop over and over and over till they achieve their goals. Robotics is a very natural example, but it's not just about robotics. Patient management, it's an iterative loop. You either encourage or force them to do something, and then from there you see where they get the state they're in. Based on the state they're in, the next treatment might be prescribed and so forth. Prevention, similarly. Maybe people could live much healthier lives if they were encouraged to do so. But how are you going to encourage them? Maybe you send them text messages on a regular basis by monitoring their behavior, by understanding what they're doing that day, and then suggesting maybe go for a walk after your lunch to get better digestion and things like that. Marketing and advertising, it's a feedback loop too. It's not a one-shot thing where you project something and you hope somebody's going to buy it. Often you build a relationship. Can we automate that? Dialogue. Let's say somebody needs something resolved. It's not about they ask something and here's the thing you're supposed to match as an answer. It's about what is it really that they're trying to resolve and how do we get to the goal, which is having resolved their issue. And optimizing operations for logistics and so forth is all long-term decision-making to make that work well. So very different kind of problems. Ultimately, often what it means is that you take in some observation, for example, pixels, and you turn it into action. Now, from a research point of view, a natural starting point is video games. Why? Because they're easy to do research with. You can't break anything in the real world by learning to play video games. So, turns out that it was possible, it was shown by DeepMind a few years ago, to train a large neural network, much like the one that was used for image recognition, but train differently, train it to output actions, and not train it from prescribed actions in situations, but train it from its own playing of the game. And it will just randomly play again, and if one of those 2 times was better, just to random luck, then it'll reinforce that with the same backpropagation to make that more likely to happen again. By doing that, you can actually get superhuman level performance on many Atari games. And the beauty here is that it's not building a system specific to any one of those games. It's a single system, and no matter which game you put it in front of, it'll start learning to play that game that is in front of it right now. Here is some of these neural nets in action after they have been trained. The original work was done at DeepMind. A lot of the kind of later work that improved it was done at also DeepMind, OpenAI, and Berkeley. Now, this might be the most well-known result in this space in deep reinforcement learning, which is AlphaGo and AlphaGo Zero. What DeepMind showed is that it's not just for video games. You can do the same thing for board games. And actually, it's a very complicated problem. Because if you think about it, how many ways can you play this game? There's so many ways to play the game. If you just try to do traditional gameplay, say, if I make this move, you make that move, try to go through all possible scenarios to conclude the right move, you never finish your calculations. But through realizing that what's really there, the board is an image with white pixels, black pixels, empty pixels, and start recognizing what are good versus bad situations, you can actually learn to play this game without having to search through all possible consequences that could happen further down the line. While DeepMind was working on gameplay, video, and board game, at Berkeley we're working on doing this for robots. So the question is, can we have a robot learn from its own trial and error to run? Now, what we're going to watch here for the first time in this session is learning in action. We've seen results of learning. We've not seen learning happen. So what do we think will happen? The neural net is set up to control the robot, but it's set up with random connections. So what's going to happen? Fairly random actions, which means it's going to fall over. But after it's fallen over a few times in different random ways, it'll reinforce that one time where it fell over just that little later, make that more likely to happen again, and that will have been one iteration. And then this process will repeat, while it's trying to optimize its score, which is distance covered off to the right. So iteration 0, it just falls over, but after 40 iterations, it falls over a little later. After 160, even later. And actually, after 640 iterations, it's able to stably run. And after 2,000, it'll be fully converged. which in real time would take about 2 weeks. So not unreasonable. I mean, most kids take also at least 2 weeks to learn to run. Now, the beauty here is that the code behind it is fully general. The reinforcement learning code is not specific to this 2-legged robot. You can run that same code for a 4-legged robot, and then it'll train a neural network to control the 4-legged robot. In fact, you can run the exact same code, and it will learn to play Atari games if you put it in front of Atari games. What's also interesting here is that traditionally in robotics, you might visit a legged locomotion lab, maybe even a 2-legged locomotion lab versus a 4-legged locomotion lab, a driving lab, a flying lab, and they're all separate labs. But the methodology behind these recent breakthroughs is general across all of them. There's no need to change code between a legged robot and a driving robot, or a legged robot that's running versus a legged robot that needs to learn to stand up. You can run the same code, and it'll learn on its own to complete the task. In this case, getting the head to standing head height is the task. Now, this is, in simulation learning, some basic skills. You can actually, if you have multiple of them, you can have them play each other, and they'll get better over time by competing with each other. Here they're practicing something like penalty kicks and goalkeeping. You can actually learn a very wide range of skills. And you can do this with real robots. So this is Brett, the Berkeley robot for the elimination of tedious tasks. And Brett is learning to put the block into the matching opening. It's learning a vision system and a control system at the same time. You're watching this and you're probably thinking, I could do it on first attempt. And I suspect probably all of you can do it on first attempt. But keep in mind, this robot is starting from 0. You've done many similar things before. Imagine you as a 0-year-old coming out of the womb. Within 1 hour, we're putting that block in the matching opening. That's essentially what's happening. The brain is starting empty and is focusing on just that one task for 1 hour and masters it. Now, the postdoc who did the work in my lab that we just watched with Brett then went to Google and scaled it up. The beauty with robots is, well, if you raise children, every child is new work to raise. If you raise robots, you can use the same brain for all robots. And so, in fact, the more robots, the less work, because they all share the data they collect and can learn more quickly thanks to all be collecting data together rather than just having one robot. And so the funny thing here is that the more robots you have, the easier the problem becomes rather than harder. So here they're learning to pick objects, which is still an open problem. They've not solved the problem fully, but it's a very important problem. Warehousing logistics, can you reliably pick things to ship them off, for example, at a company like Amazon? Now, one of the big bottlenecks in all of this is the learning time. Learning time on real robots is expensive. And so what was shown at OpenAI is that actually you can train fully in simulation. And in simulation, you can train a neural network to reliably reorient this block. Now, you might say, is it really possible to build a simulator that reliably simulates the real world? In fact, it's not possible. And for the longest time, people were not succeeding. But at some point, the conclusion was, well, how about we just give up on that? And we just build many, many, many simulators, all of them different from the real world. But if we can find a single policy that works across all simulators, it might also work in the real world. And that's exactly what happened here. Now, what I've talked about so far is deep supervised learning, is input-output pattern recognition, and reinforcement learning is about learning to achieve goals. There's another type of learning that, again, I wouldn't say is 100% prime time ready, just like reinforcement learning, not 100% prime time ready, but seeing a lot of progress, which is unsupervised learning. It's going to be deep again because it's going to internalize things into a deep neural net. And it's about learning to model data distributions. And the reason you might care is because if you first model a data distribution, what might happen is the neural net that learns to model the data distribution, for example, what images look like, by learning to generate images that look like real images, then maybe that network is ready to also learn other things about the world more quickly, transfer learning, as was talked about earlier. So what we're going to do here, instead of having a neural network that goes from image to decision, from big to small, we're just going to flip it around. And code-wise, that's trivial. You just flip around the dimensions, and you're good to go. Now, if you think about what's actually happening is 100-dimensional code goes in, so 100 numbers go in, bunch of processing, out comes an image. What do these images look like? Well, this is what they look like when you initialize your network. But what if you now train a network? You download a lot of images. You don't need to annotate them. You just download a lot of images and say, I want this network to generate images that look like real images. Here's the training in action. It actually starts generating images that look like real images. Again, through backpropagation, the signal here being, do the images I generate look real? And that realness score is effectively what's being backpropagated. This is 2016. When you look at this, you might be like, yeah, realistic images, it's a stretch. I would agree. It's much a stretch to call these realistic images. Very low resolution, not even at low resolution, perfect depictions of these animals or objects. But this was the first sign of life that this might be possible. From there, this was scaled up. And so by now, these are all fake images. So this is, none of these people exist. This is just, whenever you go to this website, you refresh, you get a picture of a new person, but a person that doesn't exist. How? Just a new random code fed in, out comes a new image of a face. Much like an artist can dream up new faces, new things in the world that don't exist, the network is doing the same thing. Now at this point, it's very hard to distinguish those faces from real pictures of real people. In Berkeley, it's a little fun project. Tingwei and Caroline did this. Said, actually, let me ask a question. Who here is pretty good at dancing? Raise your hands. Wow, very few people. It's New York. People dance here? But people are not good at dancing. OK. Well, Tingwei, Caroline, not necessarily particularly good at dancing either. But who cares? What if you can just have a video of yourself dancing really good? Most of the world will think you're good at dancing and you make the same impression. So they said, well, if we can generate all this fake stuff, we can probably take a real professional dancer, take a video of them dancing, and just translate it visually into the students dancing. And that's exactly what's happening here. So that's just a calibration motion. Everybody can do that. And then top left is source video, and the other two are fakes. There's nothing real about them. The only real one is the one on the top left. And so at this point, you might still see a few glitches there, but just like the images from 2016 were not perfect by 2019, it's hard to distinguish a fake face from a real face. This is not very far away either anymore from being indistinguishable from real images, or real video in this case. Now, some of you might say hip-hop dancing, not my thing. It's not specific to hip-hop dancing by any means. More into ballet, no problem. You can do this, you're good to go. Now, what I covered here was in the image space, but nothing is specific about images. Generating pixels, well, can just as well generate text. Download a lot of text and learn to predict the next word in some article. For example, after training on a lot of mostly Reddit data, OpenAI's GPT-2 is faced with this prompt over here. A train carriage containing controlled nuclear materials was stolen in Cincinnati today. Its whereabouts are unknown. It's not a real article. It doesn't exist out there. It can't go look up what the rest of the story is. But it's seen similar stories. And so now it's going to make something up. Well, what is it going to make up? Well, here it is. The incident occurred on the downtown train line, which runs from Covington and Ashland stations. Then a quote from a Tom Hicks, U.S. Energy Secretary. Then another quote. This reads like a real article, even though it's not real. And it's just by training on enough data to learn to predict the next characters really in a sentence. In fact, it was so realistic what was being generated that OpenAI decided not to release the model to reduce how much fake text people might be generating from it, and they've decided to do a very gradual release where a very simplified version of the model is available. People can play with that, can see if anybody makes kind of malicious use of that model. If so, find defenses to it before releasing the more and more capable models over time. So, in what we covered so far, we looked at the three main thrusts in learning that have made a lot of progress in the last few years. Deep supervised learning, input-output pattern recognition. Really works if you have some experts and good amount of data. Deep reinforcement learning, about achieving goals. It's still harder to get to work. I wouldn't say it's as prime time ready, but it is starting to work in a lot of applications at this point. Deep unsupervised learning, the way we covered it was about generating data, but really why people started working on it is the hope that then you can transfer after you've learned to generate data, you can learn to more quickly learn a new thing with the same network, and that's also starting to work. In fact, for the text generation, you can have a bunch of text and end it with a question. And if it learns to complete text that contains questions, then it'll actually try to give the answer to that question. So what are some opportunities that come to mind in this space? Well, a big one is order fulfillment. Might not strike as particularly medical at first, but the truth is for a lot of surgeries, for a lot of medication, there's big distribution centers that need to deliver as quickly as possible whatever is needed for patients and operations. And optimizing those operations are becoming more and more important to make it like next hour delivery and so forth. How do you do that? You need more advanced robotic automation than what is available from traditional automation. You need robots that can see and adapt rather than just do repeated motion. Delivery robots in hospitals, robots that can move around in buildings where there is no people, that already kind of works. If the only thing is just static environment, robots can navigate buildings, build maps and navigate them. When there are people present, it's still much harder, but it's starting to work, not perfectly by no means, but it's starting to get there. Helper robots in medical procedures that might, for example, pass equipment that a surgeon might need, or that might apply the ultrasound probe in a very systematic way that you might get more systematic measurements than people all doing their own thing. And things like the Vinci robot in surgery, of course, for now, the brain is completely the person, but you can imagine that over time, if you were to record all the Vinci surgeries done all across the world, get all that data together, then at first you could start doing anomaly detection and say, wow, you're about to do something that's very different from what any surgeon has ever done before in this situation. Are you sure? And then from there also go to the next step, which is automate some of the basic parts. And medication dosage management is another one where you have a feedback loop. If you can monitor your patient closely, it's starting to happen with insulin and diabetes, where there's much closer monitoring of the patient's current state to apply the right dosage of insulin and recommendations for food and so forth to have the patient just be much healthier than they could be otherwise. Finally, patient management at a higher level. Some companies I work with, the kind of things they look at is essentially how do we encourage people to live healthier lives? We monitor what they do. How do we give them the right suggestions so they don't turn off the app that's giving them suggestions because they're just annoyed by it? But we actually give the right amount of suggestions at the right time such that they like it and feel encouraged by it rather than frustrated by it. If beyond this session you'd like to learn more about AI, in general, actually, my main recommendation for this entire session, if you do only one thing from this, would be to subscribe to this newsletter. This newsletter is done by Jack Clark. He used to work at AI Beat at Bloomberg, and now is the communications director at OpenAI, and every Monday sends out an email summarizing the last week of advances in artificial intelligence. Commercially, technically, politically, you can skim that in 1 or 2 minutes and get a general feel for what's been happening recently. If you want to dig deeper and actually learn these things yourself, there's questions about it earlier, this is a set of pointers I would recommend. You work through all of that, and I mean, not saying you can do that quickly in a weekend, but if you actually take the time to work through all of those, each one of them maybe taking 100 hours or something to work through, you'd actually be an expert in AI if you manage to work through them in a kind of way that you really understand everything. All right, that's it for me. Thank you.
We'll take a number of questions because you will not be on the panel.
Question over there.
My name is Li Shen. I'm a computer scientist at Mount Sinai. So it's a wonderful talk, and I know that your lab has done a great job in deeper reinforcement learning. And it seems that you can teach machines to play video games really well. So my question is, has there been any progress in using deeper reinforcement learning for healthcare data, such as medical imaging?
So very good question. So reinforcement learning is about goal-oriented problem solving, right? And so for healthcare data that's images, I haven't seen it tried. Where I've seen people try to make progress in healthcare is patient management. So the encouragements at the right time, right place, that I mentioned. And I've seen it in the context of people trying to actually doing detailed physiological management. They actually build models, physical simulations of how that specific patient's body works, the metabolism of the body, to then more finely control the insulin that they're providing. So those are the two places where I've seen it. I think in general it's all about behaviors and things that are over time, where you could do this, and it works a lot better if you have a good model. So for example, for the patients with diabetes or pre-diabetes patients, the physiological models apparently are quite precise, and you have a good simulator, it works quite well. The behavioral models of the people, of what they react well to, not well to, when you give them a message about something, those models are not so good yet, and it's actually much harder to get good policies there that influence people the right way than at the pure physiological level in that particular case.
Thank you.
My question has to do with sort of the evolution of how one of these models sort of changes over time. So what if you change the goal? What happens if you have this robot that's learning to run, or I guess not a robot, but like the program's learning to run to the left, and then you say to it, okay, now I want you to run to the right. Does it remember the running, or does it like start again from not being able to get up?
So the question you're getting at, I would say, is what became a lot of focus in research a couple of years ago, because like 4 or 5 years ago, it was all about, can we solve this one thing? And then I say 3 or 4 years ago, people started thinking, can we have one system solve many problems? And so technically speaking, the way it's typically done is by doing conditioning for your neural net. So your neural net might take in an image or a measurement of the state of the robot, and might take in a statement describing what the task is. And then condition on both of those will take actions. Now, if it has only learned one thing before, and then you're given a new statement of what you want, it's going to still take a while for it to figure out what that statement means. But the thinking and the initial findings are that as you have more and more tasks on which you can condition, then the n plus first one becomes quicker to learn against than the previous ones. And so that's transfer within reinforcement learning.
Cool, thank you.
Hey, thank you very much. Those very entertaining talks. So I'm sorry to ask a little bit more of a serious question, but I'd be very interested in hearing your thoughts. The demonstration of the deep fakes in the context of unsupervised deep learning were really impressive, but I'm curious if you have concerns about the development of this technology, where we've seen the breakdown of shared narratives, a return to a rise of tribalism and proliferation of fake news, and if you feel like there's a responsibility to have some sort of concurrent development of fake detection.
So absolutely, I think AI is the most powerful technology currently being developed. And as any powerful technology, you gotta use it responsibly. And the big question is, how to prevent even just a few people who use it irresponsibly from doing a lot of damage. And I think that's a very big challenge that people in computer security are, of course, very familiar with, because that's the entire game they play. It's about adversaries trying to attack you. And I feel like the same thing is essentially true here, in that we need to really think about what is the adversarial use of all of these, and how do we prevent that, or at least detect it. The kind of tribalism you're talking about, that comes from slightly older AI systems, actually. It comes from recommendation systems, where when you search for news, you don't get the news everybody else sees. You get the news that they think you're going to be most excited about, and it'll just put you in that bubble to keep clicking and clicking and clicking. And so that was even achievable with very simple AI systems. The deepfakes required latest AI to look like they might be real. I think one of the tricky things is, for now, typically, these things are trained with a generator network and a discriminator network. So when I say you generate images, and there's a realness score, that realness score comes from another neural net that's also trained to detect fake versus real. Now, when it says fake, that's a bad realness score. If it says real, that's a good realness score. And so you're training them in tandem. Typically, for now, you cripple a little bit the discriminator network, so it's not too powerful, because otherwise the generator can't learn. But you got to imagine that as time goes by, that crippling will not be needed anymore, and at some point, discriminator and generator will actually be in full equilibrium, at which point you've been trained against detection, like you've been specifically trained to not be detectable. And so at that point, we might need different solutions. Even for now, discriminator might be able to do it, probably a few years down the line might not, at which point we might need things more like cryptographic solutions, where you say, this is generated by this author. And there's a cryptographic signature that this comes from this author. Now, that only tells you it's from that author. It doesn't tell you whether it's real or not. But then you might say, well, this author I trust, versus this other author I don't trust. And so their reputation is at stake. When they are feeding you things that are fake, at some point you'll say, well, that one's always fake. I'm not following that one anymore. But yeah, a lot of challenges, absolutely.
Thanks, but actually my question was going to be about combating deepfakes as well, so I'll change my question. What are some of the applications of reinforcement learning when it comes to patient care beyond just robotics, and are you seeing anything else that's being deployed with healthcare?
Yeah, so I think the big thing with reinforcement learning to think about is, can we build a medium reliable simulator? If there is a path to building at least a medium reliable simulator, there's a path to running reinforcement learning and optimizing a policy that might help out. So that's one path. The other path is to say, do we have a lot of data where a person's already making decisions that we're reasonably happy with, and we want to automate those decisions? And if you just do supervised learning, what will happen is you'll have a pattern recognizer. It'll try to make the same decisions as that person, but it won't understand the goals. So it'll be a good starting point. And then from that, you can do reinforcement learning to fine-tune, explore a little bit around what it's learned so far, and then learn against reward, which is final achievement, rather than against pattern matching what the person did. And so what I would look for is opportunities where either a lot of human data is available that can be bootstrapped off, or a simulator can be built in which the reinforcement learning can happen. And it doesn't have to be perfect. In-hand manipulation, none of those simulators were remotely perfect. But you had an idea of, here's a range of simulators that roughly span the kind of things that could be happening in the real world. If you train against all of them, might learn something robust that works across all of them, and then including real world.
Okay, thank you.
Well, let's thank for the questions, and Pieter.
Just want to say, if anybody has more questions today or anytime later, my email address is just available online. You just Google my name, you'll find my email address, and always curious to learn about new challenges people are interested in. And who knows, maybe we'll be working together sometime. It'll be very exciting. Thank you.